Hello, everybody. So this starts into module 5. We're past the halfway point, so we're on the end. It is Thanksgiving this week, but the school's only closed on Thursday and Friday. It used to be closed for 4 days for Thanksgiving, but we gave up those 2 days in order to get a whole week off in October. So the week off in October is really, really nice. Instead of waiting an extra month for 2 days, we get a whole week off halfway through the semester. I think that was kind of a nice trade, but it does leave us a little bit rushed if we need to travel on Thanksgiving and it has to be done on Thanksgiving morning or skip class or something. So there is class Monday and Wednesday, which is a regular week for us as far as lecture goes. Possibly a busy holiday, so if we normally do your homework on the weekend and then find yourself suddenly overwhelmed with holiday events and things, try to let me know ahead of time if things are going to be late. Otherwise, a couple big ones coming this week. Object-oriented programming, which talk about that in a while. It's been around for a while. Once computers could handle it, it's pretty much all object-oriented programming. Functional programming is the thing for history books. Fortran and COBOL, you might have seen those mentioned in history books. We don't write programming. We've been using Python, and we've been using it kind of in a non-object-oriented way. We've actually been using it as static objects. Static means there's one and only one copy, but we've been treating static objects like they were functional code. It is that we have been using objects since day one in this class. And then on Wednesday, possibly tonight, we'll start talking about GUIs, graphical user interfaces, because really at this level, we're just introducing both of them. If it was entirely up to me, I would introduce graphical user interfaces on day one of the very first programming course, because that's we hardly call it software if there's not a GUI on it. GUI, we can pronounce the acronym, so we usually do. It's really close to a very common word. But if I did that, then people who I meet for that class would be offset from every other programming class. So that would cause more problems than it would solve. But we'll get in there, we'll talk about some stuff. It's fairly straightforward, and by the time it gets introduced, people are starting to have an idea of how programs go together. So it usually also gets very, very little coverage. We'll give it a little more coverage than the typical class gets, because I think it's kind of an important thing. We make software. When you say make software, you're probably thinking about something that has a GUI on it. It's not words you type in the console, it's buttons you click on. If you type anywhere, there's a text input box to type into. The graphical interface, but that's probably Wednesday. We might get to it tonight after we talk about some object stuff. But at the same time, that might be a little bit overwhelming, and splitting those up might make more sense, because then there's time for the first bit of knowledge. And also with our textbook, they have one very short chapter on object-oriented programming, and then the next chapter is the one on GUIs, and they don't do anything except object-oriented programming for the GUI. And they take it several steps further. So it's like whoever planned out the textbook might have intended for there to be 2 or 3 more chapters of object-oriented programming between the basic introduction of classes and the advanced implementation of classes in the GUI. I think that makes the GUI stuff look harder. We'll look at it both ways, and you can use either one. I have duplicate examples, 2 programs that do the exact same thing, one of them with the class notation, and one of them with just functions and variables like we're used to using. And I've had a lot more practice with. And that way you can just look at it and see which way you want to do it. Both of them will be fine. And at some point on Wednesday, perhaps maybe next week, because there's a little bit of an opening, so we'll talk about GUIs a little bit more and get into some details on those. That's kind of an important thing. We'll eventually get to discuss where it's beneficial to use the class notation. None of the requirements in this course, whether it's the things from the book assignments this week or your final project, none of them it's not really we don't get the benefit of the class notation in those situations. They're not big enough to benefit from the object oriented. So we can skip the whole class, creating a class, and just do it with a bunch of functions and variables like register writing and get the same results. Actually, a little bit better, because object-oriented programming is bad for a computer. So let's talk about object-oriented programming. I always like to start with two pictures. And for the first one, I'm stepping away from computer stuff for a second and draw a picture that hopefully you've seen. How many people have had a biology class? Somewhere along the way. A little bit of biology, maybe in high school. Took that as your elective credit, because that almost always runs at every Ivy Tech campus because of all the health programs. That's one science we know always runs. Takes a little while before there's enough people to run a physics course. Actually, when I was getting my engineering tech degree from Ivy Tech, one of the teacher went and signed up for a physics 2 course because after years of waiting, there was we were still one short, and that included the valedictorian from Hanover. Well, the person that was supposed to be the valedictorian at Hanover got a B on the physics 2 course. So the person that was right behind them rushed over to Ivy Tech to transfer in a physics 2 course, and then her GPA was going to shoot up above this. A competitive school, and it's only a few minutes down the road. But that left those who were required to take a physics 2 course, we were only one person shy of that minimum number of students for the course to run. So then one of the teachers registered for the class, and she had to have physics to get her math degree, so she didn't need the class, but had to get that other person in there because there was a bunch of us waiting on that to get our degree. We couldn't get the engineering tech degree without physics degree. Electricity is kind of a big deal. Actually, we couldn't start taking the electrical courses until after we had the physics 2 course. And there was a whole bunch of those we had to take. But that was really nice of her, and a little complete sidestep. Not every science course runs every time, but may have encountered some biology, or really we just need one thing for biology, the tree of life. Has everybody seen the tree of life before? That general categorization, how we categorize all the various life forms on Earth. I'm going to draw it with the root at the top. There's different ways we can draw it, right? And this is a common example. We usually start seeing it early because the way that we categorize life forms is the way humans naturally categorize things. Up at the top, it's the root, so sometimes it's the bottom and the tree goes up. This is a computer class, so we're going to do the root at the top and the tree goes down. Up at the top, we have our root, just life form. Those few properties that every life form has in common. That overall definition, where no matter what it is, you can look at 2 things and say one of them's alive and one of them's not. The most basic properties of being a life form. It's actually a definition that SETI uses, Search for Extraterrestrial Intelligence, that I really like, that's along those lines. It was early in the days when they were first getting funded and set up, and somebody's grandma stopped by to visit, see what her grandson was doing after college. She was all excited about it. It was a new NASA program looking for aliens. Like, oh, that sounds awesome. And she's sitting there talking to the scientists, and they're like, they're talking about how hard it's going to be certain and confirm everything. And the old lady was like, no, it's not going to be hard. Life is squishy. That's all you need to know. And they're like, what? And she's like, they asked her to elaborate, and she's like, life is squishy. That means you'll recognize it when you see it. I always like that definition. And So did the scientists that said it. They actually made that part of their official thing. Like, that's awesome. That's the best definition of life. It's squishy. When you look at it, you'll know it's alive or not. But our general categorization that we have those most basic properties. And then as our tree grows out of that root, we add details. There's three main branches out of that root. We have archaea, bacteria, and eukarya. Eukarya. I'll spelling on that one. Eukarya, I know how to pronounce that one, but not spell it. There's most words in biology class know how to spell them, but not pronounce them. And we add a few more details about to start categorizing those things. They inherit all those basic properties it means to be a life form, and then add to it. And we keep adding layers to our tree and get more and more specific. Like from bacteria, what do we got? We got E. coli, or Staphylococcus, step. It starts with step. Very common one. The cones and the rods. They're cones and rods. I'll say that. Circles, the ones that turn purple and pink in that standard biology experiment. But we have multiple things where we add more details as we move down our tree. Same thing on eukarya. We have a couple different branches. Down one branch we might have fish, and on another branch we have mammals. And it adds details. It takes everything that it means to be a eukarya, and that already had everything that it means to be a life form, and we're going to add more details to it. The fish, we had scales and gills, the bones and stuff, so we can breathe underwater, and I'm skipping a couple steps here. Or then mammals, hair and mammary glands tend the young. We're adding details to that general description of life as we go down. Different types of mammals. Somewhere down there we'll get to humans and elephants, and obviously skipping a bunch of steps here. And they have a bunch of things in common. There's that commonality that both humans and elephants have, and that's in the definition of being a mammal. And some of it's all the way up here, just the general definition of a life form. So we inherit those traits, add more details to them, then move down the line and repeat. Now, at the next level, we inherit all that stuff and add more details until we get to every single specific life form on Earth. That's probably enough of that one to draw out. Hopefully seen that general picture before. And bring it up now, and I like to start with that from biology. Because when we do an object-oriented programming, we use object-oriented programming methods to create a program, and we make a diagram to show the relationship between the objects we created. Object-oriented programming. I'm going to talk about that acronym in a second. OOP is obvious, but if we add an S on the end, it makes it very pronounceable. It gives us a nice pronounceable acronym. We'll have a similar thing. In our language, there's something, or we have this root that is usually called object. It's called object in Python. And we're looking at it in Python. This root that defines what it means to be part of the language. Everything that goes in our language has certain characteristics. For Python, the Python interpreter has to be able to interact with it. There's a version of casting it to a string, or casting it to an integer, or equality, greater or less, and all that stuff that we do with all the things in our code. those basic traits. Those are up here at our root. So everything in Python is going to have it. So we have a similar type of structure coming off of that. Somewhere down here, we'll make an object. There's some standard examples, cars and animals and geometric shapes. You'll have cars as a homework assignment. I'll do animals. So somewhere down there, we're going to have this animal. So maybe we're making software for a veterinarian office. They need to connect their database to their own custom little GUI to keep all their patients straight. So there's an animal object that defines what it means to be one of those pets that go to that particular veterinarian office. A name, an age, how much do they weigh, previous health records, all that stuff that's defined in that. We'll talk about this more before long. But then beyond animal, there's other details we could add. We might have a feline branch, or a bird branch, or a canine branch. And felines, maybe one person has a pet lion and somebody else has a tabby cat. We took the traits that it means to be an animal, added a few more details to get a feline specific, and then we could add more details like it's really big, and get a lion or a really small one and have a orange tabby cat. But what a lion and tabby cat have in common was defined in the layer above. Same thing with canines. Different types of dogs. We could have a black lab or a beagle or a chihuahua. I don't know why I keep choosing words that are really hard to write on the board. They're all sometimes alternative. I guess there's not an alternative word. Eukarya. There's an E in there. Eukarya. Yeah, I think that's how it's spelled. An I in archaea and a Y in eukarya. That's not right. But either way, you see that pattern of how we categorize things. I like to start off with this picture because biology, this one's so common, we start showing this to kids at an early age because this is how humans naturally categorize things. And when we diagram out our stuff for object-oriented programming, we get the same picture. So that's the big advantage to it, is we get to think like a human again. Right? After all these classes and all the work learning to think like a machine, learning how to think in such a way that a machine can process it, we get to think like a human again, which is bad for a machine because machines don't process the way humans think. But if the programmer can do 1,000 times more, right? Programmer can do 1,000 times more, so plus 1,000 for the capabilities it adds to the programmer, we get a 10% loss in efficiency because it's bad, good for the programmer, but bad for the machine. Plus 999.9. The math still works out that it's worth it. The human can do so much more that it is worth the extra stuff for the machine. So I like to start off with those pictures because the way we're going to categorize and organize our code in the way that's natural for humans. The most natural way for humans to categorize and organize things. So a lot of stuff in these pictures probably don't make sense right now, so I'm gonna go ahead and erase them. But I just like to start off the object-oriented programming section by drawing those pictures side by side to just immediately show the benefit of it. It's purely for the programmer's benefit. It's entirely for the programmer's benefit. Okay, that marker is not erasing very well. Okay, so now to our actual notes. Object oriented programming. Which, again, for the acronym, it's not uncommon to add an S at the end of that. And then we have a nice pronounceable acronym, a common word actually, and we probably wouldn't have to work too hard to figure out something that works for an S then. Object-oriented programming software. That would give us that other letter so that it's a lot easier to write on the board. So that the acronym flows out a little nicer. Not uncommon, so you might see it someplace, and I think it goes nice in the notes, so I'm going to do that. So I guess the definition to start with. What it is and what it actually is kind of confuses people at first. We are creating a custom data type. A lot of people, when we start putting objects together, we put variables in there and write methods in there. And a lot of people, when we come back and use it and have a reusability thing, a lot of people first want to categorize it with functions we just looked at. But it is very, very different. A function is a variable that holds instructions. That is one piece of what we need to make an object. What you want to compare it to, make a little note here. Compare to integers or strings or floats or Boolean. That's the sort of thing it is. It's a type of data. But those are primitive data. Actually, string's not primitive data. String is a combination of characters. And characters are primitive data. One letter, but usually humans tend to go ahead and think of string as a primitive data type. That's one of our abilities. So I'll leave it on that list. But it's a type of data. A string is actually an object that's built up of primitive data. Sometimes that's not quite going to be enough for us. That example I already alluded to that we're going to do this evening. Make virtual representations of animals. Have a name, an age, how they live in. Oh wait, that's my normal classroom. An animal has a name and an age, probably a weight. It's going to make a sound. Okay. There's multiple data types there. We have strings and numbers, both integers and floating point numbers. Maybe audio files. We haven't really worked those into our Python code. It's just type of data we have for audio files. If somebody wants to see that specifically, let me know. Send me a message, and I will work it into some of our lesson plans where we see added audio files. It's much like it's the type of data that's already built into the computer. So, like our other stuff, like when we need an integer, we just say, okay, here's an integer. It kind of behaves that way, but we can take a look at it at some point if anybody wants to see that in raw Python. But it's not a hard thing to look up. There's nothing fancy with it. So we're going to create a custom data type. It was invented back in the early 60s. Invented in early 60s, 1962. I know when it was invented. Early 1962 in Norway. And I am not even going to attempt to pronounce the guy's name. I can't even tell you what letter it starts with. I can write the letter down, but y'all have seen Norwegian names, right? I'm not even gonna attempt to pronounce it because even when it's translated to English, we still don't use the English alphabet to write Norwegian names. I'm not gonna try to pronounce his name, but he invented it back in 1962. And Norway is a very, very rich country. So the early days of NATO, they had, in 1962, Norway had the nicest computer on earth. And it worked great on the nicest computer on earth. But it's good for the human, bad for the machine. There's a lot of overhead that comes with it. Most computers could not handle it. There's just too much overhead that comes with it. They burn through all our resources just wanting to do object-oriented stuff. As the years went past, I'll make a note here, too much overhead. Too much overhead. But it worked on the nicest computer in the world. But the single nicest computer in the world is not quite going to be enough. Over the years, things got better and better and better. And by about 1985, what we would call the average computer could handle it. The average computer could handle the overhead. With object-oriented programming. So it took over 20 years from the invention before it could be used. And after that, it took off like wildfire. By 1989, we rarely saw anything other than but then the 1990s rolled around, and then the whole dot-com bubble. And computers really took off and made it into everybody's household and in every classroom in all the schools. We were, by that point, we were probably 90% object-oriented programming. A couple decades later, we've non-object-oriented programming is something for the history. We misuse Python in introduction classes and treat static objects in a procedural manner in order to introduce programming. But it is still an object-oriented programming is completely dominates the field. So that's what we've been using it. It's not anything new. And there are a couple key concepts, which I probably could have started talking about on that picture earlier. You will see this repeatedly in a couple of classes. Three key concepts. The first one is encapsulation. And for our class, that's the one we want to focus on. Encapsulation. And then in the 200 level class, you'll focus a lot more on the second one. I might as well go ahead and write out the list since I'm going to mention them. Well, I'll erase them from here and talk about encapsulation, but encapsulation, inheritance, and polymorphism. I'm going to erase those last two and write them somewhere else so the notes are more organized on the board here shortly, but I'm going to go ahead and talk about all three of them. So encapsulation is the one to look at first level. And then in the 200, and we'll briefly mention the others. And then in the 200 level, you'll spend a lot of time with inheritance and setting up your objects with that. The language specific ones, so 200 to 240, where you choose a language, Java, C Sharp, Python, other. There's quite a few out there, but where you study the language specific, you'll look mostly at inheritance and a little bit of polymorphism. And then in the mobile app development course, you'll see a lot of polymorphism. Which is a really big word for a really simple concept. Polymorphism just means that a tool can be used for more than one purpose. Right? Got a marker I'm making notes with. Remember my forehead itches. Marker works great to scratch an itch, right? But would we ever say that the purpose of a marker is to scratch an itchy forehead? It just works for that purpose. The one tool has more than one, can be used for more than one purpose. A hammer is another good one. Right? Everybody knows what a hammer is for, right? Hammer's a nice heavy object, so it must be for holding down blueprints and video data constructions. We would never actually say that, but it works perfectly, right? If we're out on a construction site on a windy day trying to read the blueprints, the hammer is probably the first thing we're going to grab to hold them still. It works for that, but that's not what a hammer was designed for. More than one use from the same tool. As far as coding goes, think of polymorphism as a most extreme example we would never do is like an object to handle statistics. Somewhere in there's going to be an average stuff, right? All the stuff we need to find an average. Add our numbers together and then divide by how many there are, get the average. But one of the methods there that builds that up is a method to add a bunch of numbers together. We could use that anytime we needed to add a bunch of numbers together. That's an extreme example we would probably do, but it's not what that was designed for, but it would work fine for it. So encapsulation, you'll notice the word capsule is right in the middle. Almost capsule, there would actually be an E in that word capsule. But you can think of it like that. Close it up, seal it up, like a time capsule. Those were real popular in mid-20th century America. So in 1962, around the time object-oriented programming was being created, some kids, third or fourth graders, probably gathered up a bunch of stuff of what it meant to be alive in 1962, put it in a capsule, sealed it up, and then buried it. So everything, a sample of what it meant to be alive in 1962 is encapsulated in that box, sealed up to stay there. It's enclosed. So we'll close things up. Everything we need is included. There's something else going to be on the notes here in a second. Try to start adding pictures in a moment. Or on that biology picture I drew a minute ago, one of those bubbles said elephant. And everything, when you look at that picture, you know that everything that it means to be an elephant is somehow described in that bubble. It's encapsulated into that name, the name elephant. Large animal, the trunk, the big ears, and all those things that what it means to be an elephant is included or encapsulated into the name elephant or concept of an elephant. Inheritance is like those pictures I erased a moment ago, right? Up at the top is just the most, from biology, when it's just the most basic type of life form. What is the current definition of that? It's self-replicating, has to eat. I think there's a third thing on there, but very, very small list of properties. That is the most basic level of what it means to be a life form. Then everything inherits that and adds to it. So things come down. And on those pictures, I'm going to do a couple part of the biology picture again. So we have up at the top, we had life form. And then somewhere coming out, we had the Eukarya branch with like fish and mammals on it. And somewhere down there, we had the humans and elephants. And I'm going to draw some arrows here pointing back up. The reason the arrows point up confused me for the longest time. But all three of these are included in this categorization, this natural for humans. What it means to be an elephant is included in this bubble. Inheritance is coming down. So we take all of these properties and we inherit them and add a few more. So kind of like the way inheritance is used amongst people, right? People born, grow up, spend a lifetime working career, building up some amount of wealth, hopefully, right? Some savings. Hopefully it's enough that we would call it wealth instead of bigger savings, but what people accumulate over their lifetime. Eventually they'll pass and their kids will inherit that and add to it what they will accumulate over their life. And that process repeats, right? Eventually they'll pass and their kids will inherit what the first generation built up, and then what the second generation added to it, and then they'll add to that over their lifetime. The same way we use inheritance in here. What it means to be a life form is inherited by all eukaryotes. What it means to be a eukaryote is inherited by all mammals. And what it means to be a mammal is inherited by all elephants. And the reason the arrows point up, not down, confused me for the longest time, is we always use those arrows when talking about inheritance, but the arrows are actually polymorphism. If we need any random mammal, we have two things with those arrows, polymorphic arrows pointing, saying, okay, either one of these can behave as a random mammal. We need any random life form, anything on that chart. If we need any random human, we're kind of restricted, right? We only have the one option. So the arrows extend the polymorphism. What can one thing behave? What else can that tool be used as? These are the concepts, the ideas, how we want to think about them. It's okay if I erase that bubble again. I want to get the biology picture off there, but I probably should have talked about that stuff beforehand. So these concepts, that's that natural organization thing. That's where that builds up from. That's how humans naturally categorize things. So we can do that in our programs. I'll spread this out a little. The big one for us is going to be encapsulation. And then over your next few classes, it's going to expand because it's a very important concept. So we don't want to try to rush it all at once and just overwhelm you and forget half of it. So for the first level, think about encapsulation. Everything it means to be our data type is included. A string is an example. We were looking at that very briefly the other day. A whole bunch of methods built into a string. Well, we talked about it and then pointed towards a list because lecturing on that would be writing down the same list that's in the textbook. Y'all can read the list out of the textbook or whatever website you like the formatting. You can give the same list in lots of different places, right? And all the stuff that it means to be a string are built in. Everything that string can do. It's not like the donut picture. Because there's two things we need for our data type. We need its properties and its behaviors. So in the inner circle is properties, and in the outer circle is behaviors. And in Python, the inner circle isn't so nice and safe there. We don't actually have private data in Python, but in other languages, we can make our data fields private, where they're not accessible from the outside. But then some sort of client, the user of our software, And we saw already that it doesn't have to be a human that's using our software. Software can use other software. We've already started using the import method in our script. We're not just importing things that were in Python that when we started using it. We write our own script and then we import that into another script to use it. Right, we've already started seeing that. So the thing using it could be others. More often than not, it's going to be other software. And then a whole big chain of clients all using each other, and eventually there's a human. But the thing that needs access to it, our client can access that outer circle of behaviors, which would be our methods, the stuff that it can do, right? Like with a string. The client can access that outer set of behaviors. So like make a string all uppercase or all lowercase, or call the capitalized method. Capitalized with parentheses, and then the first letter is capitalized. I never use that on the midterm. A couple of y'all came up with some really good algorithms. Some great job on those algorithms, some nice algorithms for getting the first letter capitalized, but there is that's a common behavior we would want for strings. I thought our textbook mentioned it, but that was supposed to be done with one method. One person did a 3-line code. That project did that midterm in 3 lines. I thought that was very impressive, because it was just used a loop to repeatedly grab input, and that input automatically calculated onto the string, so the string just got built bigger and bigger and bigger after each pass through the loop. And when the very last word was just ignored, like finished or done or something, that word was ignored, and then it just printed out that big string that it built up with the dot capitalizing. Very short, very efficient. I was not trying to trick anybody up. So some of y'all, I guess, that didn't realize the capitalized method was there. They came up with very nice algorithms for figuring out how to make the first letter capitalized. But it is built in. It is just not capitalized. Because that's a common behavior we would want for a string. So that's a good example of encapsulation. All of the behaviors we want from that data type are there. And those things we saw in strings, upper or lower, or replace. Char at is a common one. So we'd say char hello world dot char at e, and it'll tell us 1 because the second index of the string has an e in it. Where do we find that character at? Oh wait, I just said that backwards. Char at would take it a number. We'd say char at 2, and then that would give us an L from hello world because the third character is an L. We also have an index of, so hello world dot index of, and there we put an E and we get back the number saying what index. I said that backwards at first. Those are common ones. But all the behaviors we want are encapsulated in there. So when we make our own data type, we want to make sure that's included. So the client can access the behaviors, and the behaviors can access the properties. Our term for that, we'll grab a different color. The properties are going to be attributes. And we store the attributes in data fields. And I remember when we were very quickly talking about relational databases, that each cell in the relational table is called a data field. And in object-oriented programming, our attributes are stored in data fields. It is not a coincidence that we use the same term there. Those things look very different in the text files where we work with them. I'll stop there. They look very different in the text file. But we use the same word, and it is not a coincidence why we use the same word. They look very different in the text file, but only in the text file. And behaviors, our term for that is going to be methods. which we've already seen methods. Functions and methods are the same thing, but methods are specifically for object-oriented programming. But we don't do anything with Fortran or COBOL in the modern world. So we pretty much don't have object-oriented programming. People still use Lisp a lot, but most people that use Lisp are using some sort of scheme variant, and that's object-oriented Lisp. So even the language that's been around since 1958, that is still in heavy use, has been modified to be object-oriented. But we have this little bubble, this capsule, and the inner circle we don't really have in Python. Does our book use the double underscores in the class examples? I haven't looked at it in a moment. Probably could have checked this before class. Let me jump on, check our textbook. There's a workaround that's pretty common in Python. We usually just skip over it because we don't have private data in Python. And some of our other languages, we can put the keyword private there, and then there's no way to access it from outside of the object. There's only internal access. But with Python, there's always external access. There's sort of a workaround where we use semi-static data fields and treat them as if they're private. So if the data fields where we hold our attributes, so basically the variables built into the object, if those start with 2 underscores, underscore, underscore, we've seen that a couple times. At the very least, we've seen it on our card statement, right? If underscore, underscore name, underscore, underscore is equal to underscore, underscore main. And people throw the 2 underscores at the end for symmetry. The 2 at the beginning mean something. They have meaning to the computer. Is it this class? We're going to look at some of the examples here. Oh, yeah. That one I clicked on, accessor or mutator. That's the correct term for multiple choice quiz. Remember, on multiple choice quizzes, like homework assignments or certification exams, it's going to ask about accessor and mutator methods. If you're talking to another program, call them getters and setters. We're either getting the value or we're changing the value or setting the value. That's how we speak to each other. But technically they are accessors. We need to access the value, or mutator, we need to mutate the value or change it. But well, we say here get retail price and set manufacturing, set model. So we call them getters and setters. If they're doing that, then they probably, here's the class. Here's an example, but I didn't see him create a class in that example. Well, they're talking about it. If the textbook shows double underscores, if you see that in somebody's Python code, act like it's private, act like it's not accessible from the outside. What you have to do is you have to type 1 underscore, then the class name, then 2 underscores, and then the data field, and then you can access it. So it's readily available, but it's a way to convey the message to other programmers that we want that data treated as if it's private. And then we'll use getters and setters methods, and we'll have behaviors to change that data so that we don't directly go to it and just reassign it with the equal sign with a variable. It's an important thing. It's hard to stress why it's important at this level, but as you do more and more object-oriented programming, well, it makes sense. But you can think of it as protecting the data. The actual data points are nice and safe there in that inner circle. And there's only one way to get to them. It's sort of the idea. So that's encapsulation. And inheritance is very similar. We'll take all of the stuff we defined here and then add more to it. So we'll start with those basic ones and add things to it. An important one some words you're gonna see with that. Am I still on the board? I guess there's a little room here. It's something called the open close principle. So our objects are open for extension but closed for modification. So closed for modification is not like a car. When we need to fix a part, we open the hood back up and take the part off and replace it. It's like a time capsule. It's sealed up. If we open it, we mess up the whole thing. So it's sealed up and has to stay there. It's closed for any modification once it's been created. If we want to make changes, we extend it into a subclass or a child class or a derived class. We have different terms we use. Parent and child, superclass and subclass, base and derived. We have 3 sets of words. You just want to mix them. You want to say parent and derived. Derived goes with base, parent goes with child, super goes with sub. So the pairs go together, but we have different ways to describe that whole thing. And we would inherit all of that stuff from the parent. If we needed to modify it, we would extend it into a child and then modify the child. And keep the original one, the original capsule sealed up. Then encapsulation there. Encapsulation is the big one to look at this time. Inheritance and polymorphism kind of come along. You will see those. We'll see it a little bit, but you'll see it a lot more. Focus on those more. First step is getting used to encapsulating the data. It's okay if I erase this side and then talk about the example, which it's 5 till 7. So we'll talk about plan out our example and then actually do the example after a break. Coming on that time. So we have talked about the international standard of communication in IT. Unified modeling language. It's a pictorial-based language so that we don't have to speak the same language in order to work together. So UML, we have for object-oriented stuff, we use what we call UML class diagrams. I believe they're included in your homework assignments. Basically, it looks like a big box. UML class diagram. And up at the top of that box, I have a little section with the solid, lit up with a solid line that has the identifier. What is the name of it? And then we'll set up all our data fields. I'll make a few little notes on here. Minus int x minus string y. Just sort of a generic example of what type of data it is, and then what we're going to call it. And then the minus sign here means private. make a public int counter. And I'll underline that. Then we have a dashed line. So the plus sign means it's public, it's accessible from the outside. So it's in that outer circle in the donut picture. And then underline means it's static. Static means there's one and only one copy. If there's only one copy, we can go back to the blueprint, which a class is a blueprint. We'll talk about that when we start typing up the example. And then we'd have some methods. So usually methods are going to be our behaviors. So we want those publicly accessible. So down here we have, and we need to say what the method is going to return. So a public string returning method that we can call method one. I don't know. I can't think of a good name. We put any parameters in there and list out all the stuff this way, like a public integer, a public void method called method two. Because till we get to a solid example, I don't have anything to put there. Just draw the diagram. What else is missing? Oh, abstract. Method two, method three. And the pound sign means it's abstract, which we're not going to talk about in this class. That's the one thing missing from the UML diagram that we wouldn't talk about in this class, so I wanted to go ahead and mention it. So we have our identifier, the name of the thing. List out our data fields, usually they're private. If something is static, we underline it. Static means one and only one copy. So when we set up a class, that's a blueprint, a design for an object. And then when we get to our code, we make a bunch of objects out of that design. We instantiate the design into an object. But there's going to be lots of different separate ones. Sometimes we want everything to go together. Like we want a counter to count all of our animals, no matter how many we have. No matter what type of animal they are, we want one counter to keep track of everything, all of our objects. So we need, no matter how many objects we create from that diagram or from that design, we want them to all share the same counter. So if we make it a static counter, there's only one counter to go around everything. Plus sign for private, minus sign. So I just said that backwards, I'm sorry. Plus sign for public, minus sign for private, and pound sign for abstract. And then say what type of data it's going to return. So anybody can look at it and see that. For your homework, you do have to draw those. But if you look at that and think about it when you're going to write it in code, you'll quickly realize it does not require any thought whatsoever to draw that picture. No thought involved if you already made the class. So computers can generate that all day long if you write your code. And what does require intelligence is organizing it. Because you'll probably have lots of classes in your project. And they all have different types of arrows connecting them together. Some of them have solid arrows, some of them have hashed arrows. Some of them have some of them are aggregations, some of them are compositions, so they'll have different types of arrowheads on them. Lots of different lines connecting them, which means it's going to be a mess of the picture, and there's not going to be any way that we can set it up so the lines don't cross each other. I probably have an example on that I can pull up real quick. We're going to make it and just go in here, grab something so I can get to the repositories. I finally hit enough repositories that won't give me the scroll bar on that homepage anymore. So I have to go in here and get all of them. Clone tab has it, but I don't think I put it in the web app version. I think this has a UML diagram. Unless it's in here. Design, there it is. Nope, that's the ERD. Maybe that one didn't have it. I thought I did nice documentation for that one, but unless it was in the other folder. It's probably in, we go to the other one. Your teams will have it. There's no way I didn't put documentation on a project management software. I like to use project management software in my planning lectures and classes out. But project management software is usually for big projects. So sometimes it's hard to even get it down to the day. It doesn't want to go smaller than a week. But for planning lectures and stuff, I needed to go down to the minute or the second. So I had to make my own. There we go. UML class diagrams. So it's kind of hard to see against the checker background. You see all the UML class diagrams. There's a bunch of them on there, and they're all connected by these different types of lines. And there's no possible way that those are going to show up on that picture when those connecting lines not cross. The dependencies and the inheritance is just too dispersed throughout there. And aggregations and compositions and all that stuff. It's dispersed too much that there's no possible way you can draw that picture without those lines crossing. So intelligence is required to organize it and try to make it some way so that if somebody needed to look at that documentation, they could follow the lines around and not get completely lost in the mess. But for the picture itself, the diagram itself, I figure out your code and the computer can generate that. But for you all this semester, please draw it by hand. Use draw.io or something, or Microsoft Paint, or draw it on a piece of paper and take a picture of it. But please draw it by hand for our class here. I'm gonna go ahead and erase the other side here. Actually, can I erase the whole thing and then I'll draw up the plan for our example. Actually, it's probably a better time to take a break and then we can talk about the example after the break, right? Take a 10-minute break now, and then we can just do all example after the break, because now we're ready to cover the rest of this. I'll go and do an example. Does 10 minutes sound good to everybody? I see head nods in the class. So my clock on the laptop says 7:06, so we'll get back to it at 7:16. I'll see y'all in just a moment. Oh, not that button. This button.